I'm talking about maths and art, and I will claim that maths and art have very, very large amounts of things in common. They're both very, very creative. They're both highly abstract in the way that they work, and they both, I hope, give great pleasure to many people. Many of us interact at the boundaries of maths and art without even realizing it, and my jumper here is a demonstration of that, and good knitting patterns are exactly where math and art come together in a wonderful aesthetic way. I find it a little bit distressing that the way maths is taught in schools often doesn't bring out its creative side, its artistic side, or its entertaining side. And I really wish that the links between maths and art were more emphasised in schools than they are now. There are whole conferences about maths and arts, and this is the biggest one. It's called Bridges. It goes around the world every year. It's in a different venue, and it's a really big and exciting meeting. Usually when you go to a meeting, the Book of Abstracts is rather dull. It's just a list of the talks. For the Bridges conference, the Book of Abstracts is a work of art in itself. So in this lecture, what we're going to do is we're going to have a look at the way that maths and art come together in a wonderful union, and we're going to kind of take a sort of historical view, starting from quite early on and going right up to the present day. And as I warned you at the beginning, we will end up by doing some dancing on stage. Okay. So some of the earliest art, or at least I thought for a long time some of the earliest art, is Celtic art. Well, when I say earliest art, art which demonstrates clearly the interaction between mathematics and aesthetics. And Celtic art goes back a very, very long way, definitely over 2,000 years. And it was an art form which was used on buildings, it was used on monuments, on statues and other things. But I think most people associate Celtic art most strongly with the work of the monks in the 800s, 700s and round about then, that used it to illustrate the books that they wrote. And here's an indication of an example of Celtic art. This is just one letter of a book. Imagine the amount of time and dedication that must have gone into producing a book if that is just one letter. And this comes from the Book of Kells, and if you are ever in Dublin and want to visit it, it's held in a museum in Trinity College, Dublin. And this is the opening letter from the Gospel of John, and here we have this lovely piece of artwork. There are various theories as to what this is. Some people say it's a snake, but snakes don't have teeth like this. Other people think it's a lion, which has been kind of made to look a bit like a snake. But it's some sort of animal. And you can see what the monks have done is they've produced this letter with the animal head, but inside the letter is this wonderfully intricate design, which is an example of a Celtic knot. And my interest in Celtic art and its overlap with mathematics started because I became interested in Celtic knots. And what I love about this design is it's aesthetically very beautiful, it's a very powerful design, but it's also something which you can recreate even if you haven't got great artistic skill. And I often go into schools and teach the young people about Celtic knots, saying you too can produce beautiful artwork by using your mathematics. So, what's a Celtic knot? Well, primarily a Celtic knot is a knot. And a knot is a design generally produced by considering a piece of string, which is a sort of loop that you can loop together in certain ways that it doesn't come undone. And mathematicians have been studying knots for about 200 years, since it was realized that the simple act of knotting can produce wonderful designs which can be studied and are actually quite hard to understand. And mathematicians like the challenge of understanding them. And here we have all the different types of knot that there are that you can tie with a piece of string with up to 7 crossings. So the unknot has no crossings. There is no knot with 1 or 2 crossings which doesn't get untied into the unknot. But here we have 3, 4, 5. There's 2 knots with 5 crossings, 3 knots with 6, and 1, 2, 3, 4, 5, 6, 7 knots with 7 crossings. And one of the most challenging questions in mathematics, actually, is understanding the different types of knot design that you can have. After about here, the knot designs stop being terribly aesthetic, but these designs here, certainly the 3, 4, 5, and this particular one here, 7, and that one here, can be seen recurring over and over again in Celtic imagery. And these were investigated by monks as aesthetic things long before mathematicians became interested in them. And often you find when math and art interact is that you get some aesthetic design which can then be studied mathematically, and then that leads on to even more aesthetic designs later on. And we're going to see lots of examples of that in this talk. This is the simplest type of Celtic knot, or knot in general, which is called the trefoil knot. It's a knot with 3 crossings. You are all familiar with the trefoil knot because it's the basis of most other knots, including the reef knot that you use to tie 2 strings together, or the knot that you use to tie your shoelaces with if you have shoelaces. So that's the trefoil knot. So let's have some fun doing some mathematics. I'm going to show you how to draw a simple Celtic knot using some mathematical ideas, and then we're going to do a mathematical investigation of the sort of shapes that you get when you do this. So this is how you start to draw a Celtic knot. You start always with some sort of grid. That grid may be rectangular, or when we saw the grid for the shape of the Book of Kells, that was a grid which had been bent round into the shape of that animal that we looked at. Now, mathematicians never like to do something without classifying it. So we give this grid a classification, and it turns out that the most useful for classification for this is to count the number of horizontal lines, which is 1, 2, 3, 4, 5, and the number of vertical lines, which is 1, 2, 3, 4. And then we give that the classification 5, 4. And we'll see why that's important in a minute. So that's a 5, 4 grid. Here's a more complicated grid. This is a 5, 6. And this shows you the 3 stages that you need to go through to draw a simple Celtic knot. And I was actually shown how to do this by no less a man than the Bishop of Worcester at a presentation on the interaction between maths and art that was held in that Worcester Cathedral. So how do we draw a simple Celtic knot? What you do is you take the horizontal lines, and on the midpoint of each of the horizontal lines, you draw a cross where the cross has a strong diagonal this way and a diagonal which goes underneath going that way. So that's stage number 1, and we could do that on any grid that you like. Stage number 2 is you take the verticals and you do the same thing, but the key thing is now the strong diagonal goes the other way and the one that goes underneath goes that way. And then you kind of draw, you start from wherever you like and kind of follow your nose. So you do loops at the end, or U-turns if you prefer, and 90-degree turns here, following the pattern round. And if you do that, you end up with a very nice Celtic knot pattern. That looks familiar to you. The patterns like this have been going back at least 5,000 years, because they occur in the design of fishing nets. And the earliest fishing net was found in a cave in Lebanon, and it's reckoned to be 5,000 years old. And I argue that that's the earliest piece of mathematics that's actually ever been found in a cave or somewhere else. So there we have a 5-6 Celtic knot. And what's interesting about this, again, if you were doing this as a fishing net, is you can ask yourself the obvious question any mathematician would ask, which is how many pieces of string do you need to make that pattern? And if you look very carefully, you can do that with precisely one piece of string. So if you're doing that as a net, you just need one piece of string and you get this beautiful pattern. It demonstrates another feature of most Celtic art, which is that the knots which are used in the designs have what we call an under and over property, that each piece of string, it first goes over that one, then under, over, under, over, under, and you have that regularity to it. So that's a 5-6 Celtic knot which has one piece of string. Here's another one I did on a grid which had 4 horizontal lines and 8 vertical lines, and it produces this extremely beautiful picture, which I find aesthetically very nice. Quick question to the audience, see if you can see this from afar. How many pieces of string do you think that one needs? 1? Any advance on 1? At least 4. 3? I've got 1, 3, and at least 4. 28. Challenging, but not true. The answer is exactly 4. So you need 4 pieces of string. If you see, here's one here, but there's another one there, and another one, another one. So that particular piece of artwork requires 4 pieces of string. It's what mathematicians actually call a link. So a link is a knot with more than 1 pieces of string. It's also what you might get with macrame or many other types of weaving pattern. So there's an interesting mathematical question where you see where art leads to some mathematics, which can then lead to other bits of art. And the mathematical question is, in general, how many pieces of string do you need? So we saw here a 5-6 Celtic knot, which needs 1 piece of string. And there is a 4-8 Celtic knot, which needs 4 pieces of string. And here's some ones I did earlier. If you take a 2-2, so that's 2 horizontal and 2 vertical, you need 2 pieces of string. 3-2, 1, 5-3, 1, and 4-4, 4. Can anyone spot a pattern there with how many pieces of string you need for the grid that you've got? What was that? Prime numbers? Odd numbers. Suppose I had a 3-6, that would require, a 3-9 would require 3 pieces of string. Can anyone see? So I'll show you how we might study this. We could study this as though we were a mathematician. So this is how you do mathematics, believe it or not. When you do maths, I would argue, if I had to define maths, is the search for pattern. One of the reasons that maths and art are so similar, or arguably the same, is that maths is the search for patterns and art enjoys patterns. We're all looking for patterns. And when I do my mathematical research and try to understand mathematics, I basically start by doing a load of experiments and then I look for patterns. And in this case, we can do a load of experiments, which is to see how many pieces of string you need for the different types of knot. And that's the answer, and we look for patterns. One pattern is that if we got sort of numbers which are like 3 and 2, which seem to have no factors in common, we get 1. Whereas if we have 2 and 2, where we have the same factor in common, we get 2. So we might start to muse on how that works. So again, going back to how we do mathematics, we do experiments, we look for patterns, we make a hypothesis, we make some sort of guess as to what might be the answer. We then do loads of other experiments, and then we prove our results using mathematical reasoning. If you're a scientist, then basically you would do up to 4. The thing which makes maths a bit different from science is this business of proving it for every single case. Some of my colleagues might skip doing the experiments in the first place as well. They just go for the patterns. Well, the answer, in this case, is the number of pieces of string that you need is the greatest common divisor of the number of vertical lines and the number of horizontal. The greatest common divisor of 2 and 2 is 2, of 3 and 2 is 1, of 5 and 3 is 1, and of 4 and 4 is 4. And that's an interesting result, and it takes a bit of proving, and the proof uses a geometrical version of Euclid's algorithm, again going back to the artistic form. Let's give some other examples. If you had 5 and 4, 1, 7 and 8, 1, 2 and 2 is 2. This design here, which you see very, very frequently on Celtic art, and there are shops which sell Irish food, which use this as their trademark, and 4 and 8 was the one we did earlier, where you had 4. I think this is a lovely example of where an artistic experiment or looking for aesthetic qualities in art leads to an interesting mathematical investigation, which then actually leads on to many more things. You can then try it out and do many other experiments. And as I said, you can prove this using a geometrical version of Euclid's algorithm. I won't do it now because it's actually quite long. So, in terms of my own personal story or journey about maths in art, I went to a Bridges conference which was held in Tunisia. It was held in Tunis, and I presented my work on studying Celtic art and gave the impression that I thought Celtic art was really old and ancient and so on. And a guy called Paulus Gerdes came up to me and said, actually, we've been studying this in Africa for many more thousand years than the Celts. And he introduced me to what's called sonar art, which is a sort of African analogy of Celtic art. It's not the same, but it has many things in common. Sorry, I'll go beyond that one. So this is sonar art. And sonar art is, as I say, art which comes from the sub-Saharan areas of Africa. And the way some sonar art works is you assume that you are creating art on the ground where you don't have paper to draw on, so you make patterns with putting your fingers in the sand or the ground and draw patterns with your fingers. And you start by doing a series of dots like this. These are the kind of basic dots that you start with. And then you draw around those dots in a kind of geometrical way to produce these beautiful patterns. And they're very similar to the Celtic patterns in that with Celtic patterns we thought of taking a grid and drawing lines or knots out of string. In the sonar art, you're drawing the picture with your finger. On the left, we have a design which is called the lion's paw. On the right, it's a somewhat more abstract design. Here's another example. On the left, you can see the actual picture, which is drawn in the sand using your finger. And on the right, here is the design. And this design is meant to be a whole load of rats that have all converged on some food and somehow merged into each other. And I was very struck when I saw these designs, when Paulus Gerdes introduced me to them, to see that they are mathematically really quite similar to Celtic designs, but have their own aesthetic qualities to them. The designs are generally done with the finger, and the person doing them would tell a story as they drew them. So many of the designs involved telling stories, typically about animals or people relating to each other. And one of the key questions that again can be asked of these designs is, can you draw them without taking your finger off the ground? These are called monolinear designs. And if you look at this one, if we start here, we go round, and we go around all the way, and that is a monolinear design so that we don't take our finger off the ground. And so one of the questions, again, mathematicians can ask is a very similar question to the one I asked earlier with the Celtic designs, is to which designs lead to monolinear and which don't. And what's interesting is that the answer turns out to be the same and shows that the Africans doing these designs were thinking mathematically in a rather similar way to the people designing the Celtic designs. And here are two of the simplest types of sonar pattern. These are where you draw your dots in a rectangular array. So this one's got 3 dots that way and 4 that way. So that is a 3-4 design. Here we have 2 dots that way and 4 that way. I'd call that a 2-4 design. And you can draw a sonar pattern. You go up, you do a loop, come round, do another loop, and so on. I love drawing these patterns when I'm in boring meetings. It kind of keeps the meeting alive for me. And this design here, you could do without taking your finger off the ground. That's a monolinear design. And in this one, you do this loop, and then you have to take your finger off, and you do this loop. And that requires 2 goes with your finger. And the number of lines that you need, or the number of loops, is exactly the greatest common divisor of the number of spots going that way and the number of spots going that way. And what's interesting is Gerda's did a lot of research into this. He found there was clear evidence that African artists stroke mathematicians who were studying these sort of things came up with a proof that this was the case, that it was the greatest common divisor, which was an artistic and geometrical proof that predated the proof that was given in Euclid's book, The Elements, by the Greeks, thus showing that mathematics was alive and flourishing in Africa many thousands of years ago. So these are 2 of the simplest designs. Here's another one which I like very much. This is called a lion's stomach. Again, that is a monolinear design, and it's different from the early ones, and it shows a lot of symmetry to it. It's got top-down symmetry, left-right symmetry, and rotational symmetry, and it's a monolinear design. But my favourite design of all, this is, if you go onto my website, you'll find this, and I love teaching students about it, is called the chase chicken. And the idea here is you have a chicken which enters a forest pursued by a fox, and it wiggles around the trees and wiggles around that tree, and then it does a lot of wiggling, and then it wiggles around this tree and wiggles around this tree, and it comes up and does a bit more wiggling and a bit more wiggling, and then comes up and a bit more wiggling here and a bit more wiggling there, and eventually comes back to where it started, by which time the fox has given up and the chicken has escaped. I just love that drawing. I mean, the mathematics that comes out of that is so beautiful, and there's so much geometry in it, and there's so much symmetry, and yet you can tell a great story, and aesthetically it's very powerful. And this is why I'm convinced that mathematics and art are exactly the same subject. So let's move forward a little bit in terms of years. So I say the sonar art goes back, we think, about 5,000 years or thereabouts. And the Celtic art goes back about 2,000 years. But there was a great flourishing of mathematically inspired art in the Islamic culture round about 800 or so on, when Islam was founded as a religion. So there was a reluctance in doing art, Islamic art. So the Islamic artists had a reluctance to portray images of people or animals, and it was felt better to create beautiful art using geometry, which allowed the people coming to the mosques and so on to sort of contemplate on the eternal nature of the universe. And I, of course, would strongly approve of anyone linking geometry to the eternal nature of the universe. This is a lovely Islamic pattern, and the basic features of all Islamic art are that you have simple patterns like the star, which get repeated, and you've got a lot of symmetry. So in this, you've got a symmetry along this line, you've got a symmetry along this line, you've got translational symmetry here, and the whole thing can be rotated around. And Islamic art starts from fairly simple things, but builds up into these glorious pictures. And here are some beautiful examples of this taken from various mosques around the world. I really wonder how they managed to do this one. It's a huge building, how they managed to create that on the building. It's such a beautiful pattern. And we know, because there's very good records, that these patterns were created using ruler and compass constructions. So the Greeks did their geometry using ruler and compasses, and essentially the same principles were then adopted a few hundred years later by the Islamic artists to create all their beautiful art here. And if anyone wants to learn more about this, in the transcript I indicate some very good websites, particularly one by Alex Bellos, who's the maths correspondent for The Guardian, who shows you how to do these beautiful, beautiful constructions. And I really like it. One of the other things I love about maths, and this is really heartfelt, and I go into lots of schools to demonstrate this, is that maths crosses across every culture. So we've seen the Celtic, we've seen the African, we've seen Islamic. It goes across every culture, and you see beautiful ideas in all cultures linking up to art. And as I said, if you look at this pattern here, the way this is constructed is we have a basic unit, which we call a tile, and then that tile is repeated in various ways, and you frequently see repeated designs. Here are some of the most commonly repeated designs that you get in Islamic art. Let's think a little bit more mathematically. There is a thing called the Euclidean symmetry group, named after Euclid, the great Greek mathematician who wrote the first textbook on geometry. And there's a thing called the Euclidean group, or E2, which is basically the ways that you can transform the plane onto itself without changing distances. So E2, E is for Euclid, 2 for 2 dimensions, because the plane is in 2 dimensions. So basically, at the risk of walking out of sight of the camera, you have in the Euclidean group translations which look something like that, where you move like that. You have reflections. Can't easily do a reflection, partly because I'm symmetric down the middle, but you also have rotations where you kind of rotate like that. And the Islamic patterns that we see here are invariant under translation. This one is invariant under translation that way, and it's invariant under translation in this direction, or a translation in that direction. So there are 3 different translations. It's also invariant under a rotation of 90 degrees. And pretty well every Islamic pattern that you'll see, these geometric patterns, look aesthetically beautiful because they have these symmetries built into them. These basic symmetries of a translation, where if you start from a point X, you go to a point A plus X, a reflection where you basically go to minus X, or rotation where M is what's called a rotation operator. That would be a matrix in normal cases. So, and the Euclidean symmetries are combinations of rotations and translations, and that tells us what sort of patterns you might look out for. Well, Islamic art, now we see it everywhere, and the most common place that we would see patterns which have these sort of symmetries built into them is in wallpaper. I'm sure you've all got wallpaper. Well, maybe not, but most of us, many of us, have wallpaper on our houses, or you can get them in curtains as well. And there's a whole class of patterns called wallpaper designs, which are the patterns which are invariant under the action of either all of the symmetries, Euclidean symmetries, or more usually what we call a subgroup, which is a restricted class of patterns. So there we have wallpaper patterns, and this one again has symmetry that way, translational symmetry that way, translational symmetry that way, translational symmetry that way, translational symmetry that way, and you can rotate it by 90 degrees. And it's those translational and invariant properties which resonate with the human brain and which give the beautiful pattern that we see. So, having realised that wallpaper was great, and by the way, in the 19th century was the great flowering of wallpaper design and production, and was deadly dangerous because they tended to make the wallpaper out of very poisonous paint, which then poisoned everyone, but fortunately those days are gone. But people, mathematicians, started studying the different types of wallpaper and came up with a quite remarkable discovery, which is there's only 17 basic designs. And there they are illustrated. Yes, you could have a design which one design could have bunny rabbits and another one could have pussycats, but the basic symmetries which those designs have, which are invariant under the Euclidean group, there's only 17 of them. It's incredible. So once you've done that, you've done it. And it turns out that in Islamic art, I suppose various constraints associated with the fact that they were on buildings and so on meant that Islamic art was restricted to only 5 of those designs. So you explore 5 of those for Islamic art, but there's only 17 of them. And I think that's an absolutely incredible result. I mean, who would have thought that there's only 17 types of wallpaper pattern? But it's a rigorous theorem which has been, was proved in the middle of the 19th century. And if anyone wants to learn more about it, you can see about it in the transcript. So one of the ways you can design wallpaper is you kind of pick your basic symmetry group and then you design the artistic patterns around that. Well, closely linked to wallpaper is the general theory of tilings of the plane. And these are, again, very good ways of producing beautiful patterns that you can put on your wall. And what is a tiling of the plane? Well, a tiling of the plane is where you take a basic unit, we call it a tile, and you fit those units together to produce a pattern with the basic premise that the pattern must have no gaps in it between the units. And the pattern that you get is called then a tessellation. And here is one of my favourite examples of all. We're going to come back to Escher presently. This is called reptiles. And this is incredibly remarkable. If you look at it, we have this one shape, which is the reptile. I suppose it's a lizard. And that shape exactly fits in with that shape. So the kind of paws fit together, the heads fit together, and so on. And there are absolutely no gaps in that. This is a basic wallpaper design as well. We have symmetries. You can see you've got the translational symmetry here, and you've got the rotational symmetry there. But just as amazingly is the way this all fits together. And again, mathematicians have spent a long time trying to understand the basic patterns that you can get, and more generally, what shapes allow you to tessellate the plane and what shapes don't. Okay. I'm not sure how Escher came up with this, but we'll see more examples of Escher's work later on. And there's a powerful link here between the aesthetics of what we see and the mathematics underlying it. Here's a somewhat simpler tiling, the Pythagorean tiling, very commonly seen on kitchen floors because you can easily make it out of wood or other materials. And this tiling is what we call a regular tiling. That's a regular tiling as well, because the pattern exactly repeats itself. If you move upwards, it exactly repeats itself. And you've got the same shape coming periodically all the time. And you see these patterns also in crystals, where you get the molecules aligning themselves. So you have tessellations and geometry and mathematics and chemistry all working their way together. And then there was a sort of question which hung around for a while as to whether every single tessellation of the plane was periodic in this manner. And it was a question which was resolved very well by Penrose, who this is Roger Penrose, and we'll see him in a minute. And he was able to prove that there were tilings of the plane which were not periodic. Now, just tell you a little bit about Roger Penrose. Roger Penrose is most famous for his work in general relativity, and he worked a great deal with Stephen Hawking and proved many very powerful results about black holes and stuff like that. For the purposes of today, he's also a former Gresham Professor of Geometry. And he discovered or invented, or whatever you want to call it, the existence of what are called non-periodic or aperiodic tilings of the plane, where we get this same tile. There's exactly two shapes here, this kind of thin diamond and this kind of thicker diamond, and they fit together to produce this tessellation. And it's got a certain amount of pattern to it, but it certainly doesn't have any of the invariances under the Euclidean group which the wallpaper had. And this was a remarkable discovery. Penrose is responsible for many other remarkable things. We'll find examples of these in a minute. And having discovered this, it's then been found that exactly the same patterns come up in many crystals, and they're called quasicrystals. So again, this is an example where art and maths fuse together to help us understand the real world. If you want to see this pattern in action, well, there's two ways. There's lots of jigsaws that you can buy, possibly even in the store here. But if you go to the Andrew Wiles building, which is the maths department at the University of Oxford, this is the pattern of the tiles exactly outside the building. There's one further type of tiling which I'd like to tell you about. So this has the same tile repeated, but in an aperiodic way. This has the same tile repeated in a periodic way. But this is a pattern which I personally really like. This is called a Voronoi tessellation, and it's an example of a random tessellation. And the way that this works is you throw a series of dots on the plane, and they're meant to be random. And then you colour the plane such that each region, every point in the green region is closer to that dot than it is to any other dot. Any point in that region is closer to that dot than it is to any other dot. This is called a Voronoi tessellation. It's not regular like the last ones, but from my own point of view, I find that just as aesthetically beautiful. I really like that. And these are incredibly useful because they're used by mobile phone providers, and that tells you if these things are mobile phone masts. Each region would tell you which mobile phone mast your phone was going to be connected up to, because it connects up to the nearest mast. So these are practically very, very useful. They're also, I think, aesthetically rather nice, and they're examples of random tilings of the plane. Right, well, we've seen a bit of Escher. So, before we get on to Escher, apologies. Again, moving forward in time a bit, we looked at Islamic art, and following on from Islamic art came the Renaissance. And the Renaissance saw another flowering of the way mathematics and art linked together. Before the Renaissance, pictures looked very, very flat. And it was realized in the Renaissance period that you could make pictures look much more realistic by seeing how you could get mathematical ideas to create an illusion of time and space, space, on a flat surface. The idea of how you can kind of project a three-dimensional image onto a two-dimensional picture. And here are some of the great pioneers. These were artists, but also mathematicians, who in the 1400s, in the Quattrocento in Italy, pioneered the idea of using perspective to allow art to become more realistic. These are, as far as I'm concerned, the people that laid the modern foundation of art as we know it, a mathematical foundation. And it was all designed on the same idea, that if you look through a window, you identify points on the horizon, we call these vanishing points, and you draw lines from the vanishing point to where you are, and that shows you how things like walls and floors could align. So this was 1400s, and a very good example of that is the Last Supper by Da Vinci that was painted towards the end of the Quattrocento, where you can see clear perspective with a vanishing point quite deliberately with Christ's head placed essentially at the same point. So there we have Renaissance art. You can even play jokes with perspective. This, by the sort of 1800s, perspective was well enough understood to draw pictures like this, which show completely absurd picture, but faked to look like it might be real. Right, well, let's move on now to the 20th century, to perhaps my favourite artist of all, which is the great Escher, who had a good long life and lived in Holland for all of his life. And Escher, to my mind, fused art and mathematics together in a way that no other artist has done as powerfully before or since. His art is full of mathematical ideas. You see tessellations, you see a lot of tricks with perspective, you see the use of mathematical shapes, and you even see the use of mathematically impossible shapes. So here he is projecting himself into a sphere by looking at the reflections. This was one of his most famous paintings. This is Day and Night in 1938. And here we can see he's got the idea of tessellations working rather well, so that we've got a bird flying that way and a bird flying that way, and they all fit together. And what's even more beautiful is that the way that the shape kind of morphs itself into the shape of the fields here. I always feel it's a shame, maybe I'm wrong, that Escher's own standing in the kind of traditional art community wasn't as high as it could be. His art has terrific appeal, popular appeal, terrific appeal to mathematicians, but I suspect less appeal to some of the members of the art establishment than I feel it deserves. It wasn't until 2015 that the first exhibition of his work occurred in the United Kingdom. I went to it, it was in Edinburgh. So that's a tessellation of the plane. Escher had worked through tessellation of the plane, discovered a whole ton of stuff, but then got kind of bored with it and decided he could do better. And here is a picture where he is tessellating the circle. And he does this by having two images. He's got angels here and devils, and he's fitted them all together so that as you go towards the outside of the circle, the pattern repeats and repeats, but gets smaller and smaller and smaller. And in principle, you've got an infinite number of devils and an infinite number of angels towards the end. How did he come up with this picture? Well, it all started at a mathematics conference. Every 4 years, there's a thing called the International Congress of Mathematics, where all mathematicians get together, and the Fields Medal, which is the highest award for maths, is presented. And at that conference, they had a little exhibition about Escher's work. And a mathematician called Coxeter attended the exhibition and was very impressed. And he wrote to Escher afterwards saying, could he use one of Escher's pictures in a paper he was writing? And that led to a correspondence which led to Coxeter sending Escher one of his pictures. And this is one of his papers that he sent him, which included this, which he'd constructed by studying what's called hyperbolic geometry. And it's that picture which inspired Escher to create that. And Escher and Coxeter had a long correspondence. They became great friends, but they never really understood each other. Let me show you. So there's a huge amount of text here, but this is, Escher wrote to Coxeter in 1958. He'd written his book, Symmetry and Generalizing. It's much too learned for a simple made plain pattern like me, but he likes these motifs getting smaller with smallest. And so basically what he was saying is he read his paper, he liked the picture, which was that one, and he's turned it into the woodcut, and this is where that picture came from. And Coxeter wrote back to Escher with that rather thing. Imagine you're an artist and you get that. Escher did his best, and he wrote to his son, I do try very hard to understand him, but never quite do. He didn't give up, and his lifelong friendship with Coxeter resulted in a lot of Escher's most beautiful pictures in the latter part of his life. Escher also work is also greatly, I wouldn't say inspired, or it kind of resonates very closely with another beautiful area where maths and art kind of meet each other, which is fractals. This is the Mandelbrot set, which is a fractal which was discovered. It's a purely mathematical object not long after Escher did those earlier pictures by Benoit and Mandelbrot. And there are very, very close similarities between that and that. And I always wonder what would have happened if Mandelbrot and Escher had actually met up, what art would have happened. Escher also worked with Roger Penrose. There he is, the same Roger Penrose that did the tiles. And Roger Penrose invented these things here, which are various types of impossible object which can't exist. They're geometrically impossible, even though they look possible. You can't have a triangle with 4 right angles, for example, 3 right angles. But Escher actually incorporated Penrose's work into some of his own work. This is Ascending and Descending, where you see this infinite staircase. And again, Escher and Penrose had a long, lifelong correspondence. And I'll give you one final example of Escher's work, which is this wonderful picture, the Pren ten Toon Stelling, which is, I think, the art gallery is its name, which has this person's looking at an art gallery, but somehow the picture in the art gallery becomes the building in which the art gallery is founded. It's got a hole in the middle. Why has it got a hole in the middle? Escher did it by drawing a basic picture of the art gallery, which is there, and then he mapped it onto this diagram here, which is an example of hyperbolic geometry, which he got from a geometry textbook, where you've got squares rotating round and getting smaller and smaller. And what he did was he took that image, combined it with that to give you that. And that's how he produced this picture. And he left a hole in the middle because he couldn't kind of work out what was going to happen there. And that hole remained for a little while until a Dutch mathematician about 10 years ago took this picture, carried on mathematically, and constructed more and more geometry into that hole, and managed to produce that picture, which is Escher's picture without a hole in it. And that's a guy called Henrik Lenstra at the University of Leiden. And if you go to the University of Leiden, the entire wall is that picture. Right, so we've done all this stuff, and I've told you about symmetries, and I've told you about the role symmetries play in Islamic art and so on. And I want to finish this talk by exploring how the symmetries work with dancing. And at this point, I do need 4 volunteers. Could I have 4 volunteers, please? All right. Yes, sir. If you'd like to come onto the stage, if we can have the lights up. And I promise you it'll only last 5 minutes, because I've only got 5 minutes left. Can we have the full lights? There we go. I need 3 other volunteers. There we go. You can be the letter A. You can hold that so people can see it. No, that they can see it. Claire, are you going to do it for me? Oh, thank you. In case you don't know, this is Claire, who kind of runs Gresham College. You can be C. And do we have a volunteer to be D? It's aesthetically nice if it was a man, but it doesn't have to be. Okay, thank you, Escher. a high percentage of Gresham staff on the thing. Can you hold those letters so everyone can see? I hope you can also see the thing as well. For those of you who don't know, possibly it's a good thing I've only got 2 more Gresham lectures to go, including this one. I'm a Morris dancer, and I've done a lot of work on studying the mathematics of Morris and related dancing, which actually is exactly the same mathematics as worked for all these other types of art. And the most famous type of English dance, I suppose, or English stroke American, is the square dance. And mathematically, we can do square dancing by looking at the symmetries of a square. So in Islamic art, we looked at how you've got these Euclidean groups acting, which produce patterns. The wallpaper produced patterns and so on. We can do the same patterns in dancing. And there's a square. And one thing we can do with a square is that we can reflect it about a diagonal. This is a Euclidean group. And that means that the square ABCD reflected by a diagonal becomes the square ACBD. I hope you can see that. The C goes to B and the B goes to C. And that's a dance move, which we call an inner twiddle. And we're going to demonstrate that with B and C changing places. Would you like to just change places? There we go. That's an inner twiddle. And if you do the same reflection back, if you change places again, you get back to where you started. And that is a reflection as a dance move. I can also do reflection down the middle, in which case A and B change over and C and D change over. So if we could do that, A and B change over and C and D, and that is called an outer twiddle. And would you like to outer twiddle back again? There we go. Doing well so far. So the other thing you can ask yourself, and this is what we did with the symmetries of the wallpaper, is what happens if you combine. So we can do an inner twiddle followed by an outer twiddle. So you can do an inner twiddle, those you two, and now do an outer twiddle. There we go. And what you should have now is CADB. And what's really wonderful is if you take a reflection of a diagonal of a square and then take a reflection down the middle, you end up with a rotation of the square. 2 Euclidean symmetries combine always to give another Euclidean symmetry. And what you've just done is rotate the square. Okay. Could you just go back to the original arrangement, A, B, C, D, and then we'll have the finale of the lecture, as it were. If you do an inner twiddle followed by an outer twiddle, that rotates the square 90 degrees. You can rotate a square 4 times, and you get back to where you start. And that shows us if we do an inner twiddle followed by an outer twiddle 4 times, which is 8 moves, you should get back to where you start. So we try that. Inner twiddle, outer twiddle, inner twiddle. That's it. Outer twiddle, inner twiddle, outer twiddle, inner twiddle, outer twiddle, and we've got back to where we started. And there we are. So there's our dance. And now it's your turn to do it. It's called a reel of 4. I won't do it to music. You are relieved. Thank you very much. No, you don't get paid. So I hope this lecture has shown you that there are really strong links between maths and art. And I just urge you to go out there and be creative and enjoy maths and art and realise that they are basically the same thing. Thank you very much.